All right, so we got this idea of special relativity, and we're going to do this by slideshow, just because there's a bunch of images that are going to be helpful to have already drawn for us. And you notice that in your notes, you're going to have a note organizer. Down one side of the notes, there's going to be pictures of the slides. On the other side of the notes, there's space for you to write, comments or whatever. Now, the comments or whatever, I may direct you and say, this is what you should write here. But honestly, this is meant to be a little bit more of a free-form style of note, where I'm going to talk about some stuff, and if you say, oh, wait, I should really make a little jot about that because I won't remember what that meant later, that's for you. So this is responsible note-taking, working with slides kind of thing. And I know that some of you have done stuff like that before, but not everybody has, right? So that's what what we're doing here, and I just want to frame that before we do it. Now let's see. Got to advance this slide. There it is. I'm a little slow. All right, so when we're talking about relativity, there's a little bit of historical background that goes on here. Oftentimes we talk about Galileo, Galilean relativity. And Galilean relativity really is what we've been talking about when we're doing, riverboat problems or airplanes in the wind. This is to say that something moving with respect to something else, while that something else is moving with respect to a reference frame or something like that, that's relative motion. It's relative. It's not like the velocity of the person on a boat, for example, is the true velocity. It's the velocity relative to the boat. And the velocity relative to the shore would be a different measurement. And so we don't talk about truth in an absolute sense in that way. We talk about observational truth, what we really see. Right? Now, there is this fellow, and here's another historical note. This fellow, I won't get his name pronounced properly, so I won't attempt it. Well, maybe I will. Olaus Romer, and somebody's going to tell me that I got it wrong because it's, your family name or something, but I can't say that name very properly. Anyway, it's like one of those Van Gogh versus Van Gogh kind of things, and I always just say Van Gogh because I can't say that however it's properly said. That's awful. Anyway, so speed of light. 2.3 times 10 to the power of 8 meters per second. Of course, this is a great accomplishment to figure out that the speed of light is 2.3 times 10 to the power of 8 meters per second, except experimentally now, we have declared that it's around 3.00 times 10 to the power of 8 meters per second. But at the same time, as a historical touchstone, first we got this idea of Galileo having relative observational things. Then we got this guy, many, many years later, saying that we got a speed to light that's on the order of 10 to the power of 8 meters per second. He's on by a more order of magnitude, right? He's at the right order of magnitude. So that's impressive, 300 million meters per second. And around 1907, we get even more accurate measurements. And so I want to, again, historical perspective-wise, let's think about this. 1907, that's before, I think, everybody in this room's grandparents were born, probably before many of our great-grandparents were born, maybe even great-great. I don't even know how long your generations are in your family, but 1907 is over 100 years ago. And we're getting to the point, by 1907, where we're figuring out pretty good approximations for the speed of light, and actually 3 times 10 to the power of 8 meters per second ends up being sort of figured out as the speed of light around that time in a vacuum. And so impressive. I also just want to point out, 1907, we have a lot of people will call what we're talking about modern physics. And I had a student last year say, well, my grandfather did special relativity in high school. And she said whatever country they were studying in, it was a Middle Eastern country. And that's where they had done special relativity for the first time. It wasn't university. And so this is something that's been kicking around for some time. So we're doing special relativity, but I hesitate to call it modern, but it does fall under the umbrella of modern. Basically, anything people have figured out in the past 150 years in physics, we seem to lump under the umbrella of modern physics. And some textbooks will even lump special relativity and quantum physics into one chapter and call it modern physics. And I think, and most textbooks aren't doing that anymore, but it's kind of silly, right? It's just a historic, why would you lump things together historically? We want to lump things together conceptually, right? So we're going to do quantum physics near the end of this course. We're doing special relativity at the beginning of this course. And so we're going to be kind of bookending this course with modern stuff. And then the stuff in between is going to be a lot of, the historical in-between stuff, more stuff that we've known about for a while, like two-dimensional collisions and mechanical stuff that relates to Newton, Galileo, things that maybe we're more familiar with in our everyday lives. But I like to have the bookends because it's nice to start with something that's like outside of our everyday experience and finish with something that's outside of our everyday experience. Now the diagram that we have here is a rough computer-generated sketch of this idea that we could have a light source where the light comes from, and I'll try to point at it with my cursor rather than my finger. We've got a light source where the light comes from. It shines towards a reflective surface. In this case, it's being shown as being an octagonal prism, reflective surface, like a mirrored octagonal shape. And that light is going to hit a mirror, come back again after it hits the mirror, and hit the reflective shape, and then go into, I mean, it's labeled as a telescope here, but we could just call it a light sensor or a light target. And so this light is going to be traveling along this path. Now, what should be the case if light just travels at a constant speed is that the light's going to go and it's going to hit that mirror, it's going to come back again. We could measure distance, we could measure time, we could figure out how fast this thing is going. V is equal to delta D over delta T. We've done all that sort of stuff before, and this seems like a reasonable thing. Now, there's other ways to deal with this in terms of the frequency and the wavelength of that light. And we've talked in sound and waves about how waves can interfere with each other, you know, through superposition of waves becoming in sync with one another and out of sync with one another. So if we could somehow fire light along a path, something like this, can you imagine that it was fired along this exact same path as another laser beam, and then they met up at the target, at the telescope that's marked there? And if they were in sync with one another, that would mean that they had traveled at the exact same speed over the exact same distance. That makes sense, right? But if they were out of sync, somehow one of them would have had to have traveled a slightly different distance or a slightly different speed to throw them out of sync. That would be a phase shift, they call it. And if they're out of sync, it could be that the peak of one wave, you know, we got peaks and troughs, and the trough of the other wave would meet up with each other, and we get destructive interference, like we talk about in the sound unit, right? And so that would mean that you get darkness. For light, destructive interference means darkness. And so if we have that fluctuation of things being in sync and out of sync, then we'd actually even would get a flicker of brightness and darkness. That's kind of cool. That would be a neat effect if we could get that to happen. And so actually, experimenters were really excited about this idea that if light's got this wave property, if light's going to be able to travel distances and we can measure distances and speed, we should be able to use a setup like this to figure out how this is all going to work. Now you can go and you can do some research into different modifications and different versions of this experimental setup. This is the Michelson-Morley experiment, is what we're kind of talking about here. And if you wanted to go down the rabbit hole of watching YouTube videos about the details of that, you can. I'm not going to go into the details of that here. What I want to present is this idea that these folks used a setup similar to this to use the properties of light and zero in on what the speed of light is. Okay? Now, we're actually stepping back, 1907 back to 1887, and this is this experiment that we're talking about. The idea would be that if we could set up an experiment like that one that I had on the previous screen, maybe a little bit more simplified, we could check to see if light can get blown off course, or if it can be speeded or sped up or slowed down. Because remember, we actually do have some idea that light has to transmit from one place to another. That's something that nobody's debating about. There was the inkling that light had wave properties that was being developed around this time. But then at the same time, if it has wave properties, people were hung up on this idea that, well, every wave we know, sound waves, water waves, any wave you can think of, skipping rope waves for that matter, needs a medium, right? Water, air, the skipping rope itself, right? Like we need a medium. And so people came up with this idea of what we call, or what became called the luminiferous ether. And the luminiferous ether is this kind of like fluidic material that is between the planets. It's kind of all around us right now. And it would have to be there if light's a wave, under the model that they were working with. It would have to be there if light's a wave in order for light to get from the sun to us, for example. Or it would have to be here in this room right now if the light's going to be transmitted from a light bulb to me. Somehow this luminiferous ether, which isn't water and isn't air, has got to have to be there. You guys follow what I'm saying? So this luminiferous ether, and oftentimes when you see ether in like a video game or something like that, ether means like mystery magic fluid or something. So this ether, this like mystery magic fluid that we can't seem to get our hands on. And you know, we really can't seem to get our hands on it because if we could have like a tangible hands-on grasp of this luminiferous ether, you imagine like what would happen if somebody waved their hands in front of a flashlight? Wouldn't it make like the image would wiggle around, right? Like you'd have light swirling because of luminiferous ether being disturbed. But it was something that was really being floated. It's an important thing because we really did believe the light had wave properties. By the way, we still believe it has wave properties. But they believed that it needed to have a medium. And of course, you guys have been brainwashed by modern science to believe that there really is a vacuum in space. But consider that you're in a generation where that hasn't happened yet. So we had to like investigate this thing. So hey, the idea goes that if the Earth is going around the sun, orbiting around the sun, there will be points where if the luminiferous ether is moving, even slowly like a river, wouldn't it blow the sun off course just a little bit? Think Galilean relativity, right? You know, river boats. And even if the luminiferous ether was stationary, somehow we were in a pond of luminiferous ether, and you know, we disregard the idea of the expanding universe, you know, then wouldn't the Earth be flying through that stationary luminiferous pond? And if you've ever tried to throw like an, you know, I had a friend throw me a banana out the window. We were doing a charity car wash. He tosses me a banana out the window. And you know that banana is going to feel drag as it flies out the window, right? There's going to be some sort of effect. Even if you drive through stationary air, if your vehicle's in motion, the banana's not going to land properly. It's going to travel, you know, differently than expected. And so if we fire light off from Earth or even on Earth while in a stationary luminiferous pond, then things are going to happen that are a little bit funny, right? And we've already acknowledged that material objects like you and I can't cause perturbations or swirls in the luminiferous ether, and that's why flashlights don't get all swirly. So, boy, this is like a lot of imagination work. And so this imagination work, which really is based on the need for there to be a fluid for a wave, is something that needed to be tested. It begged to be tested. And if you don't test it, then you're really just making up nonsense, right? It might as well just be Dungeons and Dragons out here, luminiferous ether. All right, so we've got this setup. And this setup, let me talk it through. We've got a source of light. Now, today times, we would use laser. But remember, lasers hadn't been invented until, or wouldn't be invented until, what was it, like the 1970s, right? That's why Star Wars it's like so sci-fi to have lasers. But like, lasers wouldn't be invented until the 1970s. So here we are, like 1887. So they use a narrow beam of light from a light source. And in grade 10 science, we've used things like ray boxes for doing optics experiments. So think something like that. This light's going to travel. It's going to hit what we call a half-silvered mirror. And I'm going to suggest to you, if the copy on your page isn't bold enough, can you add in these arrows so that you have the details? And as I talk this out orally, make sure that this makes sense to you. So the light's going to travel along this yellow path. And then it's going to bounce along the purple path up to a mirror that's at the top of this sort of cruciform, this cross-shaped apparatus diagram. It's going to bounce off of a mirror at the top and come right back down again along that rebound purple path. And the fact that this is called a half-silvered mirror is important because a half-silvered mirror is like one of those, you know, like the witness protection mirrors that you see in the detective shows or whatever, where the light can go, you know, only one way, but then it can also be reflected off of one surface. So it's going to get reflected off of this surface because there's half silver on one side and half silver on the other side. Half silver means the light, you know, sometimes bounces through and sometimes passes through because it's half silvered. So we're going to have this light along this rebound purple path is going to pass through, at least some of it will pass through, and hit the detector. That's the yellow to purple path. The yellow to green path is going to not reflect on its initial incident strike with this half-silvered mirror. It's going to be the light that passes through on the initial strike. It'll pass through and it'll hit the mirror that's at the end of the green path. And then it'll rebound back off that green path and it'll hit the half-silvered mirror. And yes, some of it will get transmitted through, but some of it will also get bounced back to the detector. And of course, the way that this apparatus has been set up, the half-silvered mirror is at a 45-degree angle. Now this is a modified, simplified, knockdown version of the Michelson-Morley experiment. Michelson-Morley experiment has a little bit more detail than this, but this is a nice, friendly one to look at. I really do encourage you to look at a YouTube video to see a more complex version of it, because this is my quick storytelling version. All right, so here's the thing that we need to consider. If we set this apparatus up on Earth, and if Earth is flying through the luminiferous ether, it stands to reason that at any given time, couldn't the green path or the purple path be affected by the flow of the luminiferous ether differently? If there's a crosswinds on the green path, it could blow it off course. If that's not a thing, if light doesn't get blown off course, then at the very least, the purple path is going to have a headwind working against it one way and with it the other way. And that could throw it out of phase. It could phase shift it, throw it out, waves out of sync with what's going to happen with the green path. And either way, what we're going to find is that if that luminiferous ether is a reality and we're moving through it, isn't there going to either be, at the yellow point here at the detector, isn't there going to be either the light hitting at a different spot or hitting out of phase? Seems logical? And the thing is, what do you think they find every single time they do this experiment? Is it ever hitting at a different spot or out of phase? No. All right, so that was like my big preamble. That was my huge explanation for a failed experiment. And I think even on your page here it says that it failed, right? So and it's actually a good example of a hypothesis that seems reasonable. Medium is necessary for a wave, and yet we have this thing that we have called light that has wave properties, and I'm careful to say wave properties, not to say that it's like a physical wave. It has wave properties, which is true. And that gives rise to some things in quantum physics that we can talk about later. It has wave properties, but it doesn't need a medium. And light's special in that way. Yep?
So does that mean there isn't a luminiferous?
That's exactly what it means. There's no luminiferous ether. It's not a thing. If there was a luminiferous ether, we'd have to rethink a lot of stuff. And you know, that happens from time to time in different areas of physics and different areas of science. We realize that whatever it was we thought must be true isn't true. Oh, when it comes to postulates, we've got some postulates here. Now, these postulates are things that we're going to state, and I want you to sort of digest them. So the laws of nature are the same in all uniformly moving reference frames, or frames of reference. That postulate's written on your page, but I want you to unpack it, make sure that it means something to you. The laws of nature are the same in all uniformly moving frames of reference. What that means is that if you're not accelerating, or the frame of reference in which you find yourself is not accelerating, everything should behave, and I'll say in quotes, as normal, right? Think about it. If you're in a train, you're traveling in a commuter train, and you throw a ball up in the air, if the train is moving at a constant velocity, non-accelerating, an inertial reference frame they call it, then the ball's going to go up, and it's going to come down, it's going to land in your hand, from your perspective. If the train is just turning on the gas, it's accelerating, and you throw that ball up, where's the ball going to land? Behind or in front of you? Behind you. It's going to get left behind, right? And so that would be a non-inertial reference frame. That would be a reference frame where you're not moving uniformly. And so we would say, okay, well, the laws of physics are going to seem to behave differently from your perspective. That's this postulate. Now, there are other phenomena that you might observe that would behave differently, but that's one that I can think of that's nice and tangible, right? Like it would feel like things are different. You want to try playing pool, play billiards, you know, like a little bit of snooker on a pool table. As long as that pool table in the train, remember we're still in a train, as long as that train is moving at a uniform velocity, you could play pool. But as soon as the train starts accelerating, you can't play pool effectively anymore. Think if it's coming to a stop, all the ball is going to roll to the front of the train. If it accelerates, all the ball is going to roll to the back of the train. If it turns a corner, centripetal acceleration, all the ball is going to roll to the side of the train. Any non-uniform velocity, the balls aren't going to behave the same as if you were playing in the local pool hall, right? Pool is a great example because it's a very physics-driven game. You need to have inertial reference frame be there. All right, so the speed of light has the same measured value for all observers regardless of the motion of the source of the observer. This is a weird one. And here we got an example of a spacecraft, but before we talk about the spacecraft, I want to think about what that would mean, like again, in like a throwing model. If this was true, at the low speeds that you and I live in, if you had a truck and you drove your truck and your friend sat in the truck throwing tennis balls at other friends that were along the sidewalk. Think, you're driving your truck at 60 kilometers per hour and your friend can throw at 40 kilometers per hour. And you're driving along a major street and the truck is driving 60 and your friend is throwing at 40. How fast are the balls going to impact the sidewalk friends that are catching the ball? Shout it out. Truck is driving 60, your friend can throw at 40. How fast? Starts with an H. 100. 100. It's going to smack into your friends that are catching at 100 kilometers, or 100, did I say meters per second or 100 kilometers an hour? 100 kilometers an hour. Actually, that's a pretty fast tennis ball, right? And so it's a good safety tip to not throw tennis balls while you're in a truck or something like that, because you could probably just like lob it and really do some damage to somebody. And in fact, the banana that got thrown at me, it was a friendly toss. Here I am, thankfully doing a car wash, and I had a hose to hose myself down. Thanks a lot, Dave. But the banana, just like a big old explosion. And I know that that wasn't the intention because Dave was a nice guy. But that additive Galilean relativity is a thing that we're very familiar with. But if this second postulate was true at our scale of observation, think about what it would mean. It would mean that if I was in a pickup truck driving at 60 kilometers an hour and somebody throws a tennis ball out at 40 kilometers per hour, the tennis ball is going to land in my friend's lap at 60 kilometers per hour. And as soon as I say that, you're like, what? That's stupid. That doesn't make any sense. That's outside of my experience. And I want to, after having said that, back up and talk about the second postulate as it relates to light. What we're saying is that if you have a spacecraft that's traveling at 0.9 c, and by the way you're going to read 0.9 c, this 0.9 c on the screen, is 90% of the speed of light. That's what that means. So if you want to make a little note to yourself, 0.9 c is 90% of the speed of light. And if this spacecraft, if you're into Star Trek or Star Wars or whatever, fine. Picture that, 90% of the speed of light. And you got your Star Trek spaceship moving along at 90% of the speed of light, which apparently in Star Trek isn't very fast because they can just like travel between planets or whatever. But at 90% of the speed of light, and you turn on your headlights, and you know that your headlights are going to shine off of your spaceship at c. And so if I say that the headlights shine off at c, that would be the speed of the photons, the light, leaving the headlights. But then, I know all that as a fact. 90% of the speed of light is my vehicle. I shine off this light at c. This is like the person in the truck throwing baseballs. And my baseball mind thinks, that means that the photons are going to fire off of this spaceship at 1.9 c if somebody in a nearby planet looks at my spaceship headlights. You see how this is the sidewalk, friends? And yet, if I say that light travels at 1.9 times the speed of light, doesn't that automatically break your brain? Doesn't that seem silly? And so what we say is, hey, in all reference frames, the speed of light is the speed of light. That's what this postulate really says. Doesn't matter whether you're on the spaceship and you're shining your headlights, you see that light traveling at c, 3 times 10 to the power of 8 meters per second. If you're on a planet and the spaceship flies by and you see the headlights, you'll see the headlights traveling at 3 times 10 to the power of 8 meters per second, c. And that doesn't sit well with me, and it doesn't sit well with a lot of people, because I can imagine baseballs being thrown off of pickup trucks. I'm just a simple man. You guys on board with this? Because we're all like simple in that way, right? But this is something we got to wrap our heads around. This is an important thing. This is one of the ideas here, one of the postulates. All right, so if I wanted to take a look at this and really math this out. Now, I would suggest to you do a little bit of handwriting on the math on this one. So up on the screen, it's going to be digital. I myself am not a big fan of just typed math. And so if you feel comfortable rewriting this by hand, just to make sense of it in your own brain, then please take a second to rewrite this in your own brain. We've got speed is equal to 0.9 c plus c. That would be the Galilean relativity. just 0.9 c plus c. That would give us 1.9 c. But we've got this relativistic, we'll call it an adjustment factor, that we're going to throw into the denominator. We would say that the speed of light would be 1 plus speed 1, which is a 0.9 c, times c, which is the speed of light, so v1 times v2, divided by c squared, which is the speed of light. And if we simplify that, then we end up saying, okay, well in the numerator we've got 1.9 c. In the denominator we've got 1 plus, and then if we deal with that 0.9 c times c divided by c squared, notice that that's going to be 0.9 c squared divided by c squared. And we get 1.9 c in the numerator, and the denominator we end up getting, oh, those c squareds cancel out. Those two c squareds in the denominator cancel out, and it just becomes 1.9. And then, oh, shucks, the 1.9s cancel out. And you're just left with c. And the speed of that light coming off the headlights ends up being c. And some people are like, oh, witchcraft. Well, it's an adjustment factor. Okay, and we're going to deal with that with these special relativity things. We'll deal with these adjustment factors. We'll deal with length transformations. We'll deal with time transformations. We'll touch a little bit on momentum and things like that. Even that E equals mc squared that everybody's heard so much about, there's actually something missing from that that has an adjustment factor attached to it. But you know, we'll touch on some things. And people say like, oh, why are we doing all this stuff in high school if we're going to just be given the adjustment factors without deriving them? And there's a very important answer to that, and it has to do with brain plasticity and sort of like getting as many big ideas into our brains as we can. And there's some good research that says that sometime in your early 20s, your brain elasticity starts to get like a little bit less malleable, you know? And so I think one of the big reasons, beyond the fact that it's cool and physics is cool, one of the reasons I think that we're going to get as much relativity surface information in right now is so that before you get out of high school, you have a good solid belief in this stuff being a thing, even though it doesn't fit with my brain's perceptions of baseballs and pickup trucks. I want to get as much of this stuff into my brain while my brain plasticity is at a maximum. Because if I can believe in it now as much as possible, I've got that belief embedded in my worldview before my early 20s, and your brain starts getting all, you know, unplastic, a little bit more solidified. You know, I'm old, my brain isn't as plastic as yours, and I always do my best to be open-minded, and we can always try to do that, but we can't fight biology, right? Not in that way. So we want to make sure we get as many ideas in as we can. So please embrace this as much as you can, because we've got great evidence for it. We're not going to derive a ton of stuff, because we don't necessarily have math skills for it at this stage, but we are just going to like explore what the implications are. So I want to make sure that that's a thing that we get. We won't do the derivations, we'll talk about implications more. Yes, sir?
Sorry, c is representative of the speed of light.
C is the speed of light, 3 times 10 to the power of 8 meters per second. And we're going to actually use 3.00 times 10 to the power of 8 meters per second, but that's on your equation sheets. Now, if we were going to disregard the idea of special relativity, and we were going to embrace the idea of exclusively Galilean relativity, that's the one where we would say, hey, if somebody walked at 2 meters per second on a 25 meter per second boat, then your speed would be 27 meters per second. If you wanted to take the Galileo scale of things, you know, the everyday human life scale of things, and you can try this. I mean, I'm not going to do it right now, but if you wanted to, plug in the 2 meters per second and the 25 meters per second as V1 and V2. By the way, the c squared in the denominator has to stay there. But if the c squared in the denominator has to stay there, think about what would happen in the denominator. If I have V1 times V2, 2 times 25 is 50, yeah? 50 divided by 300 million squared, what does that fraction essentially become? 0. And so people say, well, how come we don't recognize this whole thing when we're throwing baseballs? Because the denominator ends up just being 1. That's all. Because we're not fast enough. That's it. Right? And people say, well, is there a situation in our human engineered lives where this shows up? Well, actually, yes. It turns out that satellites in orbit around the Earth do start to get up to a speed where we actually care. And we'll talk about time dilation, we'll talk about mass dilation, and it turns out that time dilation, we're talking about speed right now, but time dilation, if we don't account for this stuff, all of our GPS satellites are going to be just off by enough time that the accuracy of our location finding is going to be useless. We need this. We actually really need this. If we don't deal with the mass dilation factor, actually it's momentum dilation factor, all of our particle accelerators are not going to be able to make sense of things when we smash atoms in the Large Hadron Collider or whatever. This stuff actually matters. So it's not that it's going to affect how you throw baseballs out of pickup trucks, but it is going to affect how we investigate the larger world around us, or even navigate the world around us when it comes to GPS. Okay, so there's application here. I like to know that there is an application because sometimes physics seems like so abstract and beyond, my everyday. And sometimes that's good. Sometimes it's good to explore the weird and wild that doesn't actually apply. But in this case, it really does. There's like a quick application. Yes, ma'am.
So both of these are true, but then you'd only use the Einstein's relativity if it's dealing with like the speed of light, and everything else you'd use the first one.
Yeah, so both of these, well, the bottom one is more true,
Okay.
but the bottom one is cumbersome if we're not going to go fast. Right? Like, I mean, they're both going to end up giving you the same result for the sailboat, but it's too cumbersome. It's not worth it. So yeah, it's a payoff issue. So I mean, the fact that it doesn't matter, it'll this V1 over, V1 V2 over C squared is going to disappear in sig figs in everyday life. Then there's another question. What was the other question?
I just thought it's labeled. You have to go right.
Oh, okay.
No, it's construction.
Is it?
Just construction outside? All right. All right, so I'm going to just kind of skip past this because I've talked about it. Just this new idea. And we're doing a little bit of dancing. We've talked about luminiferous ether. We're talking about how this idea of speed and relative speed and Galilean speed is something that's maybe up in the air and needs to be rediscussed. We also want to talk about simultaneity. And simultaneity is another one of those things where you'd think we could all agree that two things just happened at the same time. That, at least that is something that we can all agree on. But no, we can't. So it turns out, actually, Einstein's famous for these things. We now call thought experiments. And we actually just did a thought experiment. We talked about people throwing baseballs off of a pickup truck. Thought experiments are designed to let you think out what you could do and investigate in your own imagination how the world should play out. Okay? So this is one of those thought experiments that Einstein might have engaged in. Now, I mentioned trains and pool tables earlier. Remember, the expansion of the train lines was something that was happening big time, like 100 years ago, even a little bit before that. And so people were really invested in understanding how trains work. So it's not just that trains are my favorite thing or something like that, but some of these thought experiments center on trains, okay? For that reason, and because some of this learning is couched in history, right? And so we have some great minds that are developing their thoughts along the train line, I suppose. So we've got this train that's moving past us. So I'm going to just lean on this classic thought experiment, a train that's moving past us, and here we are. Let's just put ourselves in the position of the observers. This observer is watching their friend go past in a train, and something happens. There's a lightning strike. 2 lightning strikes! The question is, did they strike at the same time? And that's actually what's up for debate. Because, oh my gosh, lightning never strikes in the same place twice is what they say. But they never mention, does lightning strike at the same time in 2 different places? Weird. So we got these 2 events. That's all it really is. Lightning is an event. So this event happens at either end of the train. And we got a little bit of narrative here. We got this observer that's watching the train go by. Lightning strikes both ends. The observer, that's us. We conclude that both ends were struck simultaneously. And you look at it, you say, hey, look, wouldn't the light travel from this lightning strike at the speed of light, c, and hit our eyes, and the light would travel from this lightning strike at c and hit our eyes, and if the distances are the same, because I'm mid-train, boom, pow, simultaneous, no argument, how could anybody cut through that, right? But wait, notice that there's a v vector on the train. That train's in motion. It's moving, honey. And if this train is moving, think about what would happen to the light coming from the front of the train. It takes a finite amount of time to travel. We already assessed that it has speed. And it has to travel distance. But you notice that since the train is moving, isn't the light from the front of the train going to encounter the person first? Or the person's going to encounter the light first, if you think of it as a rippling light wave? Can you imagine that? Like ripples on a pond. The ripples are going to get to the person in the train first from the front of the train. And they're going to come to the person second from the back of the train. So this person that's in the train is going to see which lightning bolt first. Yeah, the front, right? People pointing to the front. So now we got this issue of simultaneity not being true. It's true for somebody at the front, or sorry, that's riding the train, but it's not true for some, sorry, I said that the wrong way around. It's true for somebody who's watching the train, you and I, but it's not true for somebody who's riding the train. And so simultaneity becomes a relative observation as well. Weird, right? So we got velocity being something that could be a relative observation. We've got timing, when something occurred, being a relative observation. And if you wanted to go, again, down the rabbit hole on this one, I would suggest looking up YouTube videos on light cones. Make a note of that, light cones. Light cones is a nice one to look into. It's not something that's a part of our core curriculum, but it's something that would definitely get discussed either in a first year or second year special relativity course. And beyond that, it's just a cool thing to think about. Because these light cones, and you'll see it if you watch a video on it. I got a link online. You can take a look there. Takes a look at our universe as an XY plane, and it extends out space-time as the z-axis. And it thinks about how cones of light would travel through time and space. So I won't go any further into that, but the slope of those cones is the speed of light, and that's something that you would want to take a look at, okay? So I'm going to not talk about that anymore, but I really would suggest you take a look at it if you're somebody who's a curious mind. All right, so the observers moving with respect to each other may not agree on simultaneous events, but both are quote-unquote right. And so there's always these people that say, well, what's the true answer? Well, the true answer, again, is relative. It depends on your perception of the universe. We're talking about how we see the universe. And truth is really a measurement of how you take in the information around you, right? And so here we've got two different people. They're both experiencing, and I don't want to get too philosophical about this, they're both experiencing their own truth. But they are both taking in the realities of the universe in different ways. And they can't agree because they're actually moving through the universe in two different ways. And what we're going to see is that people that move through the universe in different ways will experience different realities. I mean, again, that sounds very philosophical, but we're going to math it. We're going to calculate it, okay? So time will move differently. Simultaneity will move differently. Velocity may be different. Momentum may be different. Like all the length will be different. And so this idea of even time being different. I like this one. This one is a nice, friendly, it's actually the only derivation I think we're going to do here. It's a nice, friendly derivation. And it's actually based on Pythagorean theorem, which I think, that's lovely. Isn't it nice to, pull in something from ancient Greece and, arguably even before ancient Greece, Pythagoras just slapped his name on, and we say, hey, special relativity this thing. I think that's pretty neat. All right, so on the screen, there's going to be some math, but on the board in person, I'm going to do it by hand, and I'm going to suggest that you folks, again, you have some white space in your notes. I'm going to suggest that you write this out by hand, because what I've heard in the past, and what I really believe to be true, is that when you can write this in by hand, it starts to get into your brain, what's going on, okay? So I'm going to narrate, but I'm also going to write, and I'm also going to have it come up on the screen. But before we do that, let me just see what's happening here. I've got a person in the top image, and this is their perspective on an experiment that they're doing. They've placed a light source at the bottom of a spaceship, in the belly of the spaceship, and they put a mirror at the top of the spaceship. And this is really a fancy clock. Basically, time gets measured as the light travels from the light source at the bottom and smacks into the mirror at the top. We all know it's going to bounce back down again, but it does that, right? However, from an outside observer's perspective, this first picture is the guy in the spaceship. This is you people watching it from outside. So you guys are from the observer perspective, and we really do call it the observer perspective. See the O here in the subscript? Observer. This P in the subscript actually stands for proper. I mean, you could think of it as passenger, but it's not. We call it proper. So the proper perspective is the perspective as viewed by somebody who's moving along with the experiment. Okay, so this person is moving along with the experiment inside the spaceship. That's the proper time that it takes for light to travel from the floor to the ceiling. And so you notice we've just copied and pasted that from the first picture, and we put it down here in the bottom picture as this sort of narrow black line. But what you guys are seeing from your perspective is this big, bold green line and this big, bold blue line. Now, the big, bold blue line is the speed times time that you observe. The speed is the speed of the spaceship. You can make a note of that if you like. The speed is the speed of the spaceship. And the TO is the amount of time that you all experience when you're watching that light bulb travel from one position to another. And of course, why would we multiply speed times time? Because speed times time is distance. So that V times T sub O is the distance from one light bulb position to the next. Meanwhile, the light travels from that light source up to the reflector on the surface. And it must travel at the speed of light, which we discussed earlier as one of the statements that we're going to claim as something we can hold on to. And it's going to experience the same amount of time that you and I experience as we observe it, because we're watching it do this. This is something that's being observed from our perspective. And you know, this light travels from here and travels diagonally and hits the mirror from our perspective. And people say, well, how does it know to do that? Well, how does a baseball know to follow a parabola when you throw a baseball up and down on a bus? It does. It moves along with, right? So here we got this triangle that gets formed. And what we've really done is we've superimposed the observations of somebody in a spaceship traveling with the experiment and the observations of people watching the spaceship, you folks, okay? So now we've got ourselves a triangle, and by definition we're going to claim that this is a right-angled triangle, and since it's a right-angled triangle, we should be able to do Pythagorean theorem on it. So this is where the Greek stuff comes in, right? So we've got this information. I'm going to handwrite this if you want to follow along in handwriting, but it's also in typing. The speed of the light times the t observed, that's the time observed by you and I, that's the hypotenuse, equals the legs, as they say in math class. Speed of the spaceship times time observed squared plus speed of light times time experienced by the passenger. That's not really P for passenger, P for proper, and O for observed. We've got this nice, sweet little Pythagorean theorem. And then we just square all of those brackets. So we say the C squared TO squared equals V squared TO squared plus C squared TP squared. And trust me on this one. Trust the process. We're gonna do some collecting of terms and some making of sense of things, okay? And then we say, okay, well, we're gonna bring all the TO terms over to the same side of the equal sign. C squared TO squared minus V squared TO squared equals C squared TP squared. And if you like the typing, you can follow the typing. If you like the handwriting in real space, you can follow my handwriting. And I don't know about you, I just find handwriting to be more organic and like easier to read in math, but we're all different. But then we got a TO squared that we can factor out. TO squared times C squared minus V squared is a left behind binomial equals C squared TP squared. And then if we really want to, we can divide both sides by C squared. If you divide both sides by C squared, we really could, we don't do this very often, we're dividing both the binomial, well, the whole left-hand side by C squared. That's going to eliminate the C squared from the right-hand side, and what it's going to do to the binomial is going to be TO squared, open bracket, well, C squared over C squared is 1, minus V squared over C squared. So 1 minus V squared over C squared in that binomial bracket is equal to TP squared. And people usually don't leave it like that. What they usually do is they'll leave the TO all by itself, so isolating for TO. Now the reason they isolate for TO is because usually you're not in the spaceship. And actually, usually it's not a spaceship. Usually it's a subatomic particle that's moving really fast. So we don't usually like watch spaceships that are traveling at nearly the speed of light. Usually we watch particles and particle accelerators moving at very high speeds, right? So that's why we're going to isolate for TO, because like practically it makes more sense. So then we say, okay, well, as observers that are outside, we're going to say TO is equal to TP squared divided by 1 minus V squared over C squared. And then that TO squared was squared, so we're going to square root both sides, and we get TO equals the square root of all that stuff. So TP squared just becomes TP, and then in the denominator we end up getting 1 minus V squared over C squared. And again, kind of like that speed equation that we had, we've got like an observed time and a proper time, or in this case a passenger's time, that wouldn't be the same. The passenger is going to experience a different amount of time than you people watching them. And there's a correction factor that's going to be able to let us calculate that. And the cute thing about this, the thing that I think is lovely, is that it's based on those postulates about C being C any way you look at it, especially, assuming the spaceship is moving at a constant speed, and Pythagorean theorem. And that's cute. I love that. Like, it's just like, makes me feel like, yeah, okay, I can wrap my head around this, and I can believe in it a little bit more. And that's partly why I'm doing this derivation, so that we can just say, yes, this all comes from a sensible place. We won't derive all the stuff, because it does become a bit laborious, and I do want you to base some of this just on trust so that we can explore that brain plasticity. But I want you just to see that, yes, it comes from somewhere that's very logical math-wise. All right, so now there's another thing. This 1 over square root of 1 minus V squared over C squared actually is something that shows up so commonly in special relativity that we call it a gamma factor. So we can call it the Lorentz-Fitzgerald transformation factor, or we can just call it the gamma factor. This gamma is 1 divided by the square root of 1 minus V squared over C squared. And so there'll be a lot of times if you look online and you see that TO is equal to gamma TP, that means the same thing. TO equals gamma TP, and a gamma just looks like a fish standing on its head, or a sideways alpha, or however you want to conceptualize that. So up on the screen here, just in case you didn't jot it down, TO is the time experienced by an observer that is moving with respect to the thing being observed. In this case, as a spaceship flies past us, we're in relative motion relative to it, right? We're watching it move past us, as opposed to the proper time, which would be somebody that's moving along with the spaceship. That's the passenger in this case. Now the annoying thing is that our textbook, and I haven't seen anybody else write it this way, uses, instead of using proper, they use S for stationary, and they'll use M for moving with respect to, which is the observed, is O. I'm going to stick with the O and the P, because most textbooks and online resources you see will use the O and the P, because those are the traditional subscripts, okay? So I'm mismatched from our textbook in that way. And so I'm just putting this up on the screen right now so that you can see how our textbook states it. Put in this yellow stick-it note. Our textbook, instead of saying O, is going to use M. And our textbook, instead of saying P, is going to use S. And the only reason I'm not going along with our textbook on this one is because a lot of you will have tutors, you'll be online, you'll be asking AI, and all those other places will use O and P likely, okay? All right, so what does this mean? It means that the person in the spaceship, as opposed to us, if they travel in a spaceship for a long time, what's going to happen to the amount of time that they experience compared to us? What do you think? Let's go back to that equation for a second. Let's look at this red equation in the bottom. And one of these thought experiment type approaches is to say, what happens in the extremes? If I was going to, in the extremes, think about that V in the bottom right-hand corner in red, if that V becomes really, really big, like let's say that it becomes 90% of the speed of light. Could you guys please take a minute, sub in 0.9 c, 90% of the speed of light, into that V. Remember, it's got to be 0.9 squared. And could you also, let's just see, let's make TP, the proper time, the amount of time experienced by the spaceship flyer, let's make it be 1 year. 1 year. The spaceship flyer flies for 1 year, so just make it be a 1 in the numerator, 1 year, and make the V squared become a 0.9, so it's 0.9 squared, so the 0.9 is squared, and the C is squared. 0.9 C squared. Somebody help me out. The person who's watching the spaceship, the TO, how much time will they experience while the spaceship flyer, at 90% of the speed of light, travels for 1 year? Is there anybody quick on the draw? 155? Is it 1.55 or 155? 155? Anybody else get that? Exactly. What are we calculating again? Okay. So I'm going to put it on, I'll put it in the whiteboard. Sorry, people on video won't be able to see this. TO is equal to TP over square root of 1 minus V squared over C squared. Let's let TP be equal to 1. 1 year. Let's let V be equal to 0.9 squared C squared, because that's what it would mean to square 0.9 C. What does the TO end up being, Brian? 2.29. 2.29. That sounds more reasonable. 2.29 years. So how about that? If you have somebody who travels at 90% of the speed of light in a spaceship for 1 year, the rest of us left behind on Earth going to experience 2.29 years. That's what special relativity actually says. This isn't make-believe. And people say, well, really? Does that happen? Have we tested it? Actually, it turns out, remember I said things about satellites and orbits and it actually being applicable? It turns out that if you send a satellite into high-speed orbit around the Earth and you put an atomic clock in that satellite, which they do, it becomes out of sync with the clocks on Earth fairly quickly. Wild. That's wild stuff. It's really true. Turns out that we keep on affirming this thing over and over again. Now, that satellite in orbit around Earth is also going to experience the issues of a gravity well, which would be general relativity. So that would be another thing we'd stack on top of it. Turns out that the general relativity dominates in that situation. But the idea of special relativity definitely is at play. So I don't want to lie to you with oversimplifying it. Now, we're going to wrap things up here in just a minute, so don't pack up yet. I want to just take a look at how this data plays out. Because I asked you guys to do one calculation, 90% of the speed of light, but I already did it. I already did it for a whole bunch here. So what I did was I whacked in a whole bunch of different speeds down the left-hand column of this table, all the way out to 99% of the speed of light. And it turns out that if you are in a spaceship traveling at 99% of the speed of light, and your friend travels for 2 years, then you, the observer, would experience 16 years. That's wild. Now, graphically, people say, because I know that we had a question about when would you actually use these things? When does it really matter? How fast do you have to go before we care? And graphically, you see that if I look at this graph and I follow across the red plot, it looks like somewhere around half the speed of light, traveling around half the speed of light, is when that red line really takes off. You know? I'm not saying that this isn't happening lower than half the speed of light. All I'm saying is that we might not notice huge effects until half the speed of light. Now, the satellites going around the Earth are not traveling at half the speed of light, but they are going fast enough, and we do care so much about the absolute accuracy of those clocks that it impacts things, right? But if we were going to talk about sending, actually, we're not talking about really sending people in spaceships at half the speed of light, but if we were, that's when we'd really notice age discrepancies in our friends, you know? So we'll come back to this stuff next time. I feel like we're in sci-fi mode. See you tomorrow.